All right. Hi, everyone. Thank you all for coming, for cutting your lunches short to be here. Thank you for the invitation. First, I just want to say how great it is to be at a workshop on dexterity. Because, if I just want to very quickly take a step back and look at where we've come as a field. So this is a little gimmick I used to use a while back, where I would think about robot hands along these two axes of complexity versus capabilities versus abilities. And it feels like just yesterday, it was 2010, where we had our parallel grippers that would have some capabilities. We can do some things in 2010, computer vision was starting to work, motion playing. And then as soon as you did anything with more complicated hands, you could really nothing worked anymore. We couldn't do anything really multi-fingered dexterous. There was no dexterity. And now we've really come a long way since those times. And first, we as a field, we went through this stage of getting excellent performance from these passively compliant hands, work by folks like Aaron Dollar and Rob Howe and Clément Gosselin and Lionel Berglin and Mabau. Us at Willow Garage also building some compliant hands. So we got a bit of progress using this idea of compliance, cleverly designed compliance. It's hard to get compliance to be just right. But still, for the longest time, we didn't even know how to approach dexterity. And we were so far from having a workshop like the one for today. And then, of course, kind of the learning revolution happened. We all know the watershed moment for me, the OpenAI paper on in-hand dexterity, achieved via deep reinforcement learning, trained in sim, and then domain randomization for sim to real transfer, achieved with extensive external sensing, cameras, lots and lots of them, and mocap and all of that stuff. And at about the same time, in my lab, we were pushing very hard on tactile sensing, and we were building what we call the disco tactile finger, which I've spoken about extensively, so I'm not going to talk about it today. But this tactile finger that we built in my lab circa 2017 to 2019 allowed us to do this. So this is from last year's RSS, where we had in-hand object reorientation using only tactile sensing. So there's no vision here, no mocap. This example of dexterity that we were very excited about. And it wasn't just us. There were other labs as well, where and still are pushing the boundaries of dexterity. Many are here, Haoji's work, Polkit's work, many of you also. And this is far from complete, this slide, so please, don't be upset if you should have been on this slide, but are not. But in general, we got this crazy bounce as a field. We were all of a sudden, for the first time in my recollection, starting to do really complex motor skills, something that you could call dexterity. And so much of it in the field that today we can have a full workshop on what's actual, I would really refer to as dexterity. It's not the second workshop, it's not even the first. So this was, let's say, peaked maybe in the last couple of years, where now we have these pretty complex hands, many degrees of freedom. Our hand that we did the manipulation with at 15 degrees of freedom. The shadow hand, I think it's more than that OpenAI worked with. I think, Polkit, your work that you were doing the vision-based reorientation, that one is probably also around 15 degrees of freedom or so, I would approximate. So these complex hands that now all of a sudden are very, very dexterous. And then just to really bring it all the way to today, then of course, last year and this year, we've had some really cool examples of dexterity with behavioral cloning. So I'm thinking here of, the diffusion policies work, of the Aloha work, where we have, again, what we can absolutely refer to as dexterity. It's really cool. with simple grippers, relatively simple grippers, but two of them. So a bimanual setup, even with very simple grippers, can give you really dexterous behaviors. So a lot has happened in the field over the last 15 years. I think the progress is astounding. It's a great moment to be working on manipulation. So I hope everybody here is excited. I think we've seen more progress in the last couple of years than in the previous decades combined. Don't tell the graybeards I said that. So what's happening next? Now we've had these results in the last couple of years. Where are we going next? And there are a couple of trends that I see happening. One of them is this idea that we're going to get to really incredible performance, way higher than what we've done so far, if we can figure out how to better solve the exploration problem that's inherent to these methods that we've been using so far. So, maybe large sequence-to-sequence models is one way to go. There are a lot of people working on trying to learn from videos, not of robots doing tasks, but of humans doing tasks, which is very compelling. So we have some of that work going on in my lab as well, but it's not quite ready to, for presentation. I know that some of you here are working on this as well, but that's not what I want to talk about today. Instead, I want to come back to this idea of what's the sweet spot in the design space. If we think about robotic manipulators in this space, trade-off of complexity versus capabilities, we always have this desire to achieve as many capabilities as possible with as little complexity as possible. So we kind of look at, what we've done so far and ask ourselves, what is a little bit of complexity that we can add that will give us the highest bump in performance? So along this line of thinking, I want to tell you about two projects that we have going on in the lab today, right now. This is ongoing work. It's not published. It's not even submitted yet. We hope to submit some of this to ICRA. Some of this I'm showing today for the very first time, but kind of looking at where is the sweet spot in our design space. And first, I want to start with sensing, okay? So this is, again, our dexterous tactile-based in-hand manipulation, and there you can see the tactile readings that the hand is getting live as it's manipulating. And the disco finger here is giving us contact location and normal force on all the fingers. And yes, it turns out that you can do some of these policies even with just binary contact sensing. You've seen that as well, I think, in your work. But we do find that there is an increase in performance when the tactile finger gives you contact location and normal force. There's a lot that the policy can extract from there. Okay? But if that's what we need, if what we're after is contact location and normal force, well, it turns out that if you make a couple of fairly reasonable assumptions, it's a known finger geometry, it's a single contact, it's a convex finger, convex object, it's going to be a single contact. If you assume a point contact and no frictional torques, it turns out that contact location and contact force can be derived from just knowing the resultant force and torque at the base of the finger. So if you know the wrench, the force and torque applied right here at the base of the finger, then you implicitly know contact location, contact force, not just normal. So those two are equivalent. And, even if you don't make all of those assumptions, still, I believe that knowing the 6-DOF wrench at the base of the finger can be an excellent, excellent surrogate for tactile sense. This is not necessarily a new idea. For example, Rob Platt 15 years ago at NASA was doing some work along these lines. But look, if we can get so much information from having a force torque sensor at the base of the finger, rather than, go through the effort of having a tactile finger and all of this stuff, which we can do, but it's more difficult, more complex, then how about we put a force torque sensor at the base of our finger? Do we get a lot of information, but from a much, much simpler overall design? And, there are off-the-shelf force torque sensors. This is a very mature technology. But it turns out that what's out there, what you can buy, hasn't been designed for our use case. More specifically, these, the ATI, for example, these are incredibly stiff because most times people who want to do force torque measurements don't want to introduce parasitic compliance in series with whatever it is that they're measuring. So they're making those sensors to be as stiff as they can. They also want them to be very precise. And the combination of a stiff sensor and a precise sensor, that's very hard to achieve. It means you need incredibly sensitive electronics, which is why these force torque sensors cost so much. They're so expensive for what we want to do with them. And they have this limited overload protection. Once you overload one of these ATIs, it's a paperweight at that point. I'm sure many of you here have done that. In manipulation, we like compliance. We don't need our force torque sensors to be so insanely stiff. And we also don't really need maybe for some applications, the precision that the off-the-shelf sensors give us. So we set off to build our own, which is part of the fun of being in academia, is that you want to design a force torque sensor, hey, there's nobody stopping you. So we took a very, classical approach where you have two plates, a bottom plate and the top plate with a flexure in between. Anytime a force gets applied to the top plate of your force and torque sensor, the flexure deforms. There's a displacement. Our sensors can be compliant. They don't have to be very stiff. So the displacement isn't going to be tiny. There'll be some sizable displacement there. And then it's the job of the electronics to measure that displacement. Okay, sounds pretty straightforward. We came up with some targets in terms of what we feel would be useful for us to have for manipulation. These are somewhat made up, an informed guess. Okay, so then how do we actually measure that displacement? What do we put in those electronics that allows us to measure the displacement between the top plate and the bottom plate as accurately as we can? And we tried lots of things, so you don't have to. We thought about cameras, event cameras, position-sensitive detectors, all kinds of things. And at the end of the day, we converged on LEDs. Maybe somewhat unsurprising given our previous expertise with the disco fingers, but our electronics are LEDs. More specifically, here's a CAD version. So we have a whole bunch. So think of this as an emitter LED. It's emitting light. And these are also LEDs. I'm sure many of you know LEDs not only emit light, LEDs can also measure light. Right? LED stands for light emitting diode. It's a diode. An LED can measure incoming light as well. So this LED is emitting light. These ones on the opposite plate can measure how much light they receive. And then the other thing happens, for example, this one is emitting, and these measure how much light they receive. And then LEDs don't actually emit light equally in all directions. They're very targeted. They have a cone of emission, and even in that cone, the intensity of the emitted light varies quite a bit. So you can imagine that as this LED is emitting light and all of these are receiving light, once there's a displacement between the top plates and the bottom plate, the amount of light you get at the receivers is going to change because the position relative to the emitter is going to change. Okay, so this is the fundamental concept, very simple at the end of the day. Once you have a displacement between the top plate and the bottom plate, that's going to change how the light goes between your LEDs. How sensitive are LEDs to these kinds of displacements? It turns out they are incredibly sensitive, much more than I would have thought. So we built this little test rig just to evaluate that. So there's two plates, the bottom plate and the top plate, both of them in green. And then we can displace the top plate relative to the bottom plate. We put an LED on each of them, and we look, one of the LEDs emits light, the other one measures it, and we look at how the signal changes as these plates displace relative to each other, okay? And this is what the results look like. So we're plotting the displacement, the horizontal displacement between these two plates versus how much light the receiver LED gets from the emitter LED. And the sensitivity is just insane. It's so much better than I would have hoped for. So for example, on the bottom is the zoomed in version. And you can see here that even for a displacement of 0.02 of a millimeter, you get a change in signal that is way, way above the noise floor. So the signal to noise is fantastic, genuinely better than I would have thought in a million years. So very encouraged by this, we went ahead with the overall design, where again, the idea is that we use the LEDs to measure displacement between the top plate and the bottom plate. And that's our sensor. This is the very first one that we find that is complete, the first prototype. This is roughly 2 weeks old, I would say, this prototype. So this is a brand new result. On the left is the sensor itself. It's 25 millimeters in diameter. And here we have the same sensor mounted on an ATI load cell, just for reference, with a little finger-like attachment on top. So we have this brand new in the lab. We're excited by it. We're just starting to test it. This is what data looks like. So on the top, you're going to see the ATI data, force and torque. So 3 dot force, 3 dot torque. On the bottom, you see the raw signals from the LEDs in our load cell. And the sensitivity is great. We're getting a little bit more noise here. There's some more shielding stuff that we have to work on and things like that. But really nice response and sensitivity. And we're starting to have very early quantitative data. This data is about a day old at this point. So it does look like we can train a model, tell us the force and the torque. You know, the force, we're getting less than 1/10 of a Newton error usually about half that. So we're hitting the specs that we're wanting. So this is very early days. Again, this is a brand new result. I think this is what workshops are for, to share things that are really, really hot and new. But we are excited about this idea of building a force torque sensor that has the compliance that we like for manipulation and that is super low cost compared to off-the-shelf alternatives. And we're hoping that you're not going to overload and break forever. So this is the first part of what we're doing. The second part is, okay, what will these force and torque sensors go into? They're going to go into hands. Which hands? The new hands that we're building right now, and we're designing right now. This, again, is the hand that we used for RSS last year. And the kinematics here were designed for one task and one task only. And that's that task, to rotate an object around the vertical axis in hand forever. And those kinematics are fine for that, but we want better kinematics for a wider range of tasks. So we started working on that. And first we thought a lot about, hey, what is it that we do want in terms of the kinematic abilities of the hand? And some of this, goes back decades. This idea of doing precision grasps and power grasps, it's an old idea. But there's two subtleties here that I want to bring your attention to. First of all, we can do power grasps starting from large objects, right? A large cylinder, my fingers don't even touch each other. Then we have smaller objects, and for a smaller object, if I'm doing the power grasp, the thumb is stabilizing the power grasp by overlapping with all the other fingers. And we can actually go all the way to essentially a zero volume power grasp. If you imagine a pen or something, I can have a power grasp of something infinitely small, arbitrarily small. And that's very rare in robotics, almost non-existent, that you can pinch objects, you can transition to power, and you can envelop something of arbitrarily small dimensions. I don't know of a robot hand that's capable of doing those things. And at the same time, sure, we'd like to preserve the ability to do in-hand reorientation. So how do people do this amazing thing, this zero volume, all the way maybe to a zero volume power grasp? The secret is this feature of the human hand, the thenar eminence, which is maybe somewhat underappreciated, which is this part of the thumb, the thick, meaty part of the base of your thumb that stabilizes the other fingers as you're doing a power grasp. So that's one feature that we think is important. And in fact, if you think about it a little bit, let me do a quick quiz. What's the longest finger of the hand? The middle finger is the longest finger of the hand, right? If I show you the skeleton as well, does that change your opinion? Well, if you think about it for a little bit, the CMC joint of the thumb has 2 degrees of freedom. So right here, right, has 2 degrees of freedom, independent from anything else. These joints have no degrees of freedom whatsoever. The metacarpals of the 4 digits move together. There is no independent actuation there. So I will argue that that the thumb really starts from the CMC joint, whereas the other fingers start from the MCP joints. So if you think of your thumb as starting from the wrist, where it does have independent degrees of freedom, all of a sudden it's starting to look like the thumb is the longest finger by far. Right? It's much longer than all the others. It's clearly more articulated than all the other fingers. It's got this thenar eminence, which is really important, as we were saying earlier. It's not part of the palm. You have this webbing here that connects your thenar eminence to the palm, but the thumb really is independent. It has a mind of its own. It can do whatever it wants independently of the palm. So that's telling me that, the thumb is really underappreciated for the dexterity. So, the expression all thumbs, if you say about somebody they're all thumbs, usually that means the opposite. They're not very dexterous. And I think that is 100% wrong. To say of somebody they're all thumbs should mean they're really dexterous. So this is the kind of the equivalent first in some really crude XML in Mujoko. So we have a thenar eminence, we have an extra long thumb, and we have RL policies. There's an RL policy for transferring an object from a pinch grasp, from a precision grasp to a power grasp. And then the other one is an RL policy for doing in-hand object reorientation. Okay. So how did we arrive at these? Through this iterative optimization algorithm where we kept iterating between kinematic improvements in the XML and training policies to do these things that we wanted and informing the kinematic improvements, all through this optimization algorithm that eventually arrived at what you're seeing here. Do you know the GSD optimization algorithm? Exactly. It's a very powerful optimization algorithm. As far as I'm concerned, it's fully automated. I would love to get to the point where we could fully optimize this entire loop and automate this entire loop. we're not quite there yet, but at least I'm very happy that the kinematics are being improved, taking into account what the policies tell us about the ability to train those policies. Okay, and actually, there's even one more step. There's CAD as well. Because Mujoko XML is not a real robot, you know. It's still the additional step of doing CAD if you want to make a real robot. So we've recently also thrown CAD into the loop as well, and this is the very first renders that we have. This again are roughly 2 days old, these renders, but it's the same kinematics, more or less. There are some small differences, but the kinematics here and the kinematics here are very similar. We do have the extra long thumb with the thinner eminence. And the other thing that you might notice in these renders is also that we are going to put in these force torque sensors that I was telling you about. And, you know, we did end up with good old stiff position-controlled servos in the hand and force torque sensors in the fingers. So that means that we can do force control. It's going to be admittance control as opposed to impedance control, but we can do force control. We can have compliance. We thought so much about this. You know, should we go for this paradigm, or should we go for a paradigm where you have native torque control abilities in your motors, like you're building in the eyesight game that you were showing us this morning? And that's also a very compelling direction to go. You have a whole different set of trade-offs. In the end, after a long decision process, we ended up with stiff motors, but in series, a compliant force sensor. So you can think of it as series elastic actuation if you wish. It does make for beautifully nice and compact packages and things that are easy to build. So the next step over the next couple of months is going to be to actually build these things, characterize our sensors a lot better, and see where they take us. So to conclude, that today, for this kind of, here are some ongoing things we're actively busy with, I wanted to share a couple of viewpoints in the design space that we're working on. Looking at, can we get high capabilities with as little complexity as possible? In terms of hand design, in terms of kinematics, and also in terms of sensing. And these were designed to go with each other. So we're super excited to see what we can do next. First, just even translating the policies that we're training during the design phase, but then doing new policies. Just a quick shout out to the folks in the lab, and specifically Amr, Pedro, Joaquin, Sharfin, and Dongxiao, who's not in the picture, who worked on all the things that I was fortunate enough to tell you about today. And thank you for your attention.
We have some time for one or two questions.
Hi, Matei, interesting talk. So you're moving in some sense more towards by inspiration with your cosmic community. At the same time, we have there's shadows and lines that being developed, maybe like computer, like the spoke as well. At what point do we stop so to have this nice trade-off between simplicity and capabilities?
Yes. Should I wait for the microphone? All right. Thanks, Kostas, for the question. Anybody that I've been talking to for a long time, such as you, knows that I used to hate anthropomorphism, that I used to say never go anthropomorphic with a robot hand, because you're going to copy all the wrong things and you're going to leave out all the right things. And now I guess I'm changing my mind a little bit, but I am very much trying not to copy, but to actually understand what's going on. And I didn't want it to be anthropomorphic, but I said, look, I'd like to do a zero volume power. how do people do it? Because it's so hard. As soon as I was trying to design anything CAD, XML, it wasn't working out. How do people do something like this? You go from a pinch to a big, smallest paragraphs, and that's what led us to, the stuff is longer than we gave it credit for, and it's more articulated, and you've got this bulge here that seems to be very useful. What's this bulge even called? Doesn't even have a name. Oh, it's called the theater eminence. Oh, I'm going to use that in all the talks from now on. And that's how we ended up looking so anthropomorphic, almost by necessity, rather than saying, I want to be anthropomorphic. And also, as the final point, this day and age, given that we have such exciting results starting from teleop, that's another argument for making these anthropomorphic so that they are intuitive for a human teleoperator to give you demonstrations. So I never used to believe in anthropomorphism, and I guess now I'm coming around.
We took time to
Thank you.